solar wind contributes to the hydration signature on the moon. And what I'm doing is very similar to what Aaron Zent presented yesterday and probably to what Michael Poston is going to present next. So just very quickly, there are observations of hydration features on the surface of the moon from Cassini showing different wavelengths for the absorption feature attributed to water at 3 microns and OH at 2.8. And the distribution is consistent with water sticking to the coldest surfaces, but OH being more present all over. And M cubed results are similar, where you have water not sticking very well at the low latitudes, but more at the mid to high latitudes, and OH less at the low latitudes, but kind of all over. And then there are the epoxy data that demonstrate that there's a change with the incidence angle and the absorption depth, where similar locations show different band depth as a function of time of day. And these two observations from epoxy, I want to point out that the second observation on June 9th of 2009 was when the moon was likely in the magnetotail. So any hydration you see there is probably not being implanted at that exact time that the observation was taken. And then there are really exciting results from LAMP on LRO, observing signatures of hydration that Amanda's going to talk about in 2 more talks. And but the LRO data are consistent with latitudinal and diurnal variation in the band strength. So we're going to look at solar wind implantation, where the protons come in contact with the surface of the moon, and they penetrate a couple hundred angstroms. And on their way in, they do some radiation damage, breaking apart some bonds, knocking some atoms around. They can induce a collision cascade that kicks stuff off at the surface. And the protons that are implanted grab an electron and get neutralized. And they can bond with oxygen at lattice site or damaged sites, and they can move from damaged site to damaged site on out of the grain and get released from the surface. So how much solar wind is available to do this? How much OH can you create, or water can you create? If you take all the solar wind protons over the course of a lunation that hit the moon and you convert it to water, and then you spread it across the entire surface of the moon into a global ocean, that global ocean would be, a fraction of an angstrom thick. If instead, and that's over 1 lunation, if instead you distribute it as like 1,000 ppm, it's a layer that's 160 angstrom thick. If you want to know how much there is over about a micron thickness, which is about the depth that the observations can see, you're talking 16 parts per million, which is making it very low for being able to produce an observable effect on the scale of a lunation. As for a source, you don't have enough source in a lunation to really create much of a diurnal effect. So we're going to model the diffusing implanted solar wind, assuming that it's in the form of OH. And I just want to point out that our source is the solar wind delivery, which over latitude changes by, a couple orders of magnitude. But our loss is going to be related to the diffusion time, which over latitude changes by, tens of orders of magnitude. So this is our model result of the OH concentration of that's diffusing out of a grain of regolith on the moon. This is the day side. This 0 here is the noon, and that's midnight. It's a function of latitude. And what you get is at high enough latitude, the diffusion time is longer than illumination. So you get a buildup as the sun rotates of OH. And so your concentration is flat, so you wouldn't get any sort of diurnal change because it takes longer than illumination for it to diffuse out. But at lower latitudes, the diffusion time is shorter than illumination. So you get a buildup as your solar wind incidence or flux is increasing as you rotate from dawn. And then you reach a point where the diffusion time skyrocket or plummets, I guess. And so everything that comes in is being lost. And so you get a real decrease in the concentration. And then as you get past noon, then you start building up again to midnight, and then things are pretty much locked in on the night side. But I just want to point out over here that we're getting numbers down at 10 to the -6. That's 1 part per million, which is not observable as far as I know. But there could be some issues with how the water is distributed, if it's on the surface of grains versus evenly distributed, which is what I'm assuming in my model, may enhance the signal in the IR. If we fiddle around with our activation energy in our model of diffusion, increasing it here, what happens is the latitude range where the diffusion time is longer than illumination extends, so you're going to have a broader band where it's a flat concentration, and then at lower latitudes you then have this diurnal signature. If you decrease the activation energy, you move everything down. So maybe by studying very well exactly what the distribution is with latitude and local time, we can get a better idea of what the activation energy is for OH diffusion in lunar regolith. But in order to do that, we really need to understand what the concentration is as a function of position on the moon. And with the observations that are in hand, means we need to understand exactly how the distribution on the surface of grains as opposed to spread out through the grains affects the inferred concentration levels. And also it'd be great to get more observations that unambiguously nail down what the distribution is as a function of latitude and local time. But using the approximation that I've used, you need years worth of solar wind to produce an observable diurnal signal. So direct implantation is not causing a diurnal change, but maybe migration can, photometric effects or migration may come into play. So let's look at the migrating flux where something is happening. All the protons are hitting the moon. Some of them are getting stuck in the regolith, but it's in steady state. For everything that after a certain amount of time, when the regolith's been exposed for a while, every proton coming in there's got to be something leaving, some hydrogen leaving. So what we do is we assume that water is released, and that could happen as a process like they study at Georgia Tech, Michael Poston and Greg Greaves, recombinative desorption, or perhaps micrometeorites release water that was stored as OH in the soil. So with our Monte Carlo model, we simulate the migrating flux of taking the solar wind or the diffusing, the amount that's diffusing out and then redistributing it. This is after one hop, the water comes back down. You get some on the night side. And then, thank you. You have to, then it'll stick to the surface. And while it's stuck to the surface, you can observe it. And so you have to fold in what the residence time is. On the day side, we assume that sublimation is the, or controls the residence time. And these are our calculated values here. On the night side, photolysis controls it, and these are the values here. So the overall curve is that. And this is what we get for our adsorbed water on the surface as a function of time. Here in the solid lines is our diffusing OH that I showed you before, these solid lines down here. And this is adsorbed water on the surface. And you get much higher concentrations, you get a strong diurnal effect. And this should be observable. So, you know, if we don't see something like this, then that means that the either we need to revisit the residence times, and if you have longer residence times on the day side, you're going to get stuff sticking more here. You're going to raise this part up and you're going to lower this part down. Or it's not coming out as water. So, in conclusion, the solar wind does induce hydration in the lunar regolith, and it takes many years to achieve saturation. And a model of diffusing OH out of the regolith, times that are longer than illumination are required to produce an observable amount of hydration. So either there's a difference in the apparent and the absolute water content from the observations, or direct implantation and diffusion is insufficient and migration has to be included to produce a diurnal signal. So, thank you.
We have time for questions. Carl?
Can you describe the diffusion a bit? Dana, nice talk. Can you describe the diffusion a bit? How does that process work?
I'm just using a 2D diffusion equation, and I calculate a diffusion time based on the temperature and the activation energy and the diffusion coefficient, and then I integrate that as the moon rotates, and so I assume it moves or I calculate diffusion length, and it will move that far out of the grain.
Okay, thank you.
In the back, came up first.
So a very quick question. So you say there's solar wind proton can implant and create the OH, and also I think Max Zimmerman just gave a talk. Also, there's a sputtering and can kick out the atoms. So do you include that in your model?
No, what I've done right now is I just am looking at the maximum amount that's available from the solar wind. For sputtering, it's going to be a small percentage of the source. Sputtering yields on ices are very high, but sputtering yields on, you know, just kind of damp silicates is low. So I don't think it's going to be a major thing. But what is interesting is there are observations of backscattered protons and backscattered neutral hydrogen from the Kagula and the Chandrayaan-1 and IBEX